I wanted to give you another example of projectile motion. This time where we don't know all of our initial conditions. Instead, we know what the results of our projectile were. And we'll have to figure out how to work backwards in order to find out what the initial conditions were. So here's our problem statement. One of the first things you're going to notice is that there are no numbers in this problem. I want to encourage you to solve things algebraically, and so to force you to do so in this problem, I have given you no numbers. You'll notice we're given some variables, but no numbers associated with those variables. The second thing you'll notice is that this problem, which involves a football place kicker, sounds a lot like the problem we worked out in class. In class, we were given a velocity and an angle, and we had to work out whether or not he would make the goal. Now, instead, we want to know what speed does it take to make the goal. This is an example of where we don't know what our initial conditions are. Instead, we know what the requirements of our final positions or final values are, and we need to work backwards to figure out where we started from. At this point, you should pause the video, read through the problem, and see if you can set up the problem. Draw yourself a picture. And in your picture, you want to, of course, assign variables so that you can begin to populate your equations, your kinematic equations. And then you want to, of course, write down all the things you know and all the things you don't know. There are things that we know just because this is a projectile motion problem. Some of them may be useful, some of them may not. There are things we don't know, but even though we don't know, for example, the initial velocity, we can still write down equations or relationships involving that velocity that will hopefully let us work backwards to get our initial velocity. All right? So go ahead and pause the video, work on setting up the problem, and then restart the video, and we'll go on and I'll show you how I set it up. Okay, so you should have set up the problem. Does your setup look like mine? Again, remember, it doesn't have to look exactly like mine, but it should be equivalent. Some things to think about. Did you define your positive axes? Did you draw your coordinate systems? Did you define where your zeros are? A lot of students do this implicitly when they start writing down their knowns and unknowns, but it's always good to actually write on your picture where the zeros of your x and your y's are, what your positive directions are. Did you include your acceleration vector and mark what the direction of your acceleration vector was? These are all important aspects of setting up a problem that are easily forgotten. As you look over this list of knowns and unknowns, you should also notice that even though we have an unknown initial velocity, we know how our initial x and y components will relate to that velocity. And so we can still write down an equation or a relationship for our initial components of our velocity. We've marked the unknowns. We don't know anything about our time, or sorry, about our final velocities. We don't know what our final time is either. And unfortunately, this is something that is going to be key to solving this problem, because this is going to let us bridge between x and y. So as usual, we're going to want to find out what our time is first, and that's going to be our first angle of attack. As you look over the rest of the way I've set up the problem, you should see that it looks very similar to the problem we set up in class. In fact, I think everything I wrote down is exactly the same. It's just this time we're treating different variables as knowns and others as unknowns. This is, again, one of the powers of writing things down and solving things algebraically, because we can use any values for our various variables. We can treat them as knowns, we could treat them as unknowns, and switch back and forth between them as long as we keep track of them in one problem. So take a moment now and pause the video, look at your setup, compare it to mine, and see what's different. See if you can work out why you made a choice or didn't make a choice, because that's where the learning is going to happen here. Checking back and looking at my setup, I realize I made a mistake. Maybe you caught this in your setup, but it turns out I do know what the final x component of the velocity is. Remember, in x, this is a constant velocity problem, so instead of making this an unknown, I can just write it, my velocity stays the same throughout the x component for the entire length of this problem. All right, now that we have set up our problem, we have an idea of what we want to know, we can now begin to look at our kinematic equations. Over here in the top left, top right, I have my kinematic equations. Of course, we want to choose the ones that are most useful, that'll get us to the answer the question we're actually interested in. So even though we don't know what our y component of our final velocity is, we don't care. And we're not going to use any equations that involve the y component of the final velocity. So looking at our y column, that knocks out this first equation. That knocks out the second equation. That knocks out the last equation. And the only equation we have left in y is this fourth equation. In x, this equation isn't really telling us anything new, and so we're going to have to use this first equation. Now, what's our strategy? We have written down everything we know. We've found equations that will give us a pathway to what we want to know. As we said with these kinematic equations in multiple dimensions, the real key is going to be finding time. So we want to use one of these two equations to find our time in terms of variables that we care about. I'm now going to populate these two equations with my variables, the variables that I chose. So my final x position, that was d, my distance. My initial x position, well, that is just 0. And then I have my final velocity, which is the same as my initial velocity in the x direction. So that is v naught cosine of my angle times my time. My y equation, my final position in y, we're going to set that as my height. Of course, notice we just have to be greater than that height. So when we get to our answer, we just know we have to be a little bit faster velocity than what we've solved for in order to actually clear the bar. My initial position I got to choose was 0. My initial velocity, that's this one. So that's, again, just v naught sine of theta times my time minus 1/2 g times my time squared. Oops, time squared. squared. Make sure you're not making mistakes. All right, now I have two equations, and they both involve v naught. So I have a pretty good chance of being able to solve for v naught using these two equations. The other unknown I have is time, of course. Now, I have two equations and two unknowns, so I'm guaranteed a solution. As long as these are two independent equations, and they look independent. I want to solve one of these for time in order to eliminate it from the other equation. Looking at these two equations, this one, this top one, the x equation, that one's going to be the simpler one to solve for time. So let's solve that. We get time is equal to my distance divided by v naught cosine of my angle. Now that I've got my time in terms of things I care about, I can go and I can plug it into this second equation everywhere I see a t. And at this point, there's some algebra remaining, but you should be able to plug in your value, your equation for t, and figure out what our velocity has to be. So plug your t value in here, or expression in here, and then solve for v naught. Go ahead and pause the video. Find out what the expression for v naught is, then come back and start the video again. So after some algebra and a bit of rearranging and simplifying, we get this expression. The first thing you want to do anytime you get an answer is check whether your answer is reasonable. So let's check our units. This first term has units of length, and anytime you see the cosine of an angle or the sine or the tangent of an angle, that's always a unitless quantity. So our first term just has units of length. Our second term, we're going to end up with meters per second squared, but then a square root. So we end up with square root meters over seconds. All right. This last term, we've got a tangent of an angle, that's unitless. We have a distance subtracting a distance. So we'll end up with unit of 1 over distance, but under a radical. So we end up with 1 over radical meters, or square root meters. What we want is we want to come up with a unit of velocity. We're going to multiply all these together, of course. And in the end, what do we see? We see that the square root meters terms cancel out, and we're left with just unit of length over time. Sure enough, that is a velocity. So we have a pretty good bet that this is at least a reasonable answer. Our units work out. Now at this point, some of you may be asking, but Dr. Merrill, why don't we just use the range equation? It involves the initial velocity. I mean, we should just be able to say, all right, well, the range is the initial velocity squared times the sine of 2 theta, 2 times my angle, over the acceleration due to gravity. My range, this is just my distance. I can solve that. I can find out what my initial velocity is. My initial velocity is just the square root of my distance times gravity divided by sine of 2 times my angle. And you'd be close. But remember, we have to be very careful when working with this equation. This equation, and you have to look in your book to see how it was derived under certain assumptions. The most important one is that where I begin and where I end happen at the same height. If they're not, then I have problems. Then I cannot use this equation. It does not satisfy conditions. If we do on the next slide, I'll show you. We do indeed get something that looks like this term, and so we would be close in certain situations. But there are other situations, which I'll talk about, where this would be so far wrong that you would not want to use it. I mean, you would be fired from a job. So we want to be careful when we're using different equations. We cannot use the range equation. We have to be very careful. We have to use our kinematic equations and find out what the velocity actually would be. So be careful when you're just going to grab an equation. Make sure you're using it under the proper assumptions. We have our answer. The units work out. The second thing we should check is that the behavior of our answer is what we would expect. So if we look at our problem, we would expect that if we made this distance much larger and moved our field goal out here, it would take a much larger velocity in order to make that field goal. And we can see if we increased our distance, we'd end up having to increase our velocity. We'd need a larger velocity, initial velocity, to achieve that field goal. Now, it's not quite d, because there's a second factor of d in this equation. It's actually closer to square root d. But in any case, whether it goes up linearly or it goes as the square root, we know that if we increased our distance, we would have to increase our velocity, and that checks out in our equation. The other thing we can check out, right? We can keep going. What if we were on Jupiter, where our gravity is so much larger? We would expect, again, we would need a much larger initial velocity because our ball is going to fall really fast. So we need to have a much larger initial velocity so that we can make the height and make the goal. And we see the same behavior. Again, square root g, as this term goes up, my initial velocity has to go up as well. All right, so we've seen the distance and gravity have the proper behaviors. To see the influence of the angle or the height, I'm going to do a little bit more algebraic manipulation so we can make it easier to see. If I manipulate this equation a little bit, I get something that looks like this. We still see the same behavior as we saw before, right? The root g's. Root g and root d. It's not quite root d because, again, there's still another term in there. Now we can see what the influence of the angle is. It's going to be muddied a little because there's actually two terms in the angle, but I'm just going to look at this sine term. If we just look at the sine term, that's the dominating term. We can see that sine of 2x gets a maximum at pi over 4 radians, or in other words, 45 degrees. So we will get the furthest range, or we will need the smallest initial velocity when our angle is directly at 45 degrees. If we increase that angle, we need greater velocity. If we decrease that angle, we'd actually need greater velocity. It's a little bit muddied because of this extra term, as I say. The last thing we can ask is, well, what influence does my height have? This one's a little harder, but let's look at this. I plotted something that looks an awful lot like our term there. Now we have this x in the equation. I just plotted square root of 1 over 1 minus x. And you can see, first of all, the smallest this can ever be is 1. So the smallest my velocity can ever be is this front term. And this, with this back term, this mass becoming 1. If I increase my height at all, I have to increase my velocity with it. So this is, as my height goes up, my velocity has to go up as well. But there's also some point where I will just need infinite velocity. I would need so much velocity I can't overcome it. So there's a height where it doesn't matter what my velocity is, I could never make the field goal. So we can see that if we make our field goal taller, we need a larger velocity. But interestingly enough, we also learned that there's a height at which if we make our field goal that height, we would never make the goal. This is the power of solving things algebraically. You can see a lot of the behavior. You can check your answers. Now all we'd have to do is plug in our values, and we could get some numerical solution for our initial velocity. But we have an idea of what our answer should be. And even better, we have answered every question for any velocity, for any initial condition, any height, any distance. We now know what the answer will be. So you now have an example of how we can work backwards. We can work with relationships even if we don't have all of the known values. We started out and we said we wouldn't know the initial velocity, but we were still able to come backwards and find out what that initial velocity would be. We showed what the power of solving things algebraically was. Not only can we find our answer, but we can find the answer to any question involving these variables. And we can check ourselves and make sure that our variables have the proper behavior. We can check our units. And now all we would have to do is put in our numbers. You're going to need to master these skills. I won't demand that you will simplify your answers like this all the time. But you may want to practice being able to do it, doing these manipulations, because they will help you see whether or not your answer is reasonable. Well, good luck, and I will see you in class.